Okay, so this problem reads, a football quarterback runs 15 meters straight down the playing field in 2.5 seconds. He's then hit and pushed 3 meters straight backwards in 1.75 seconds. He breaks the tackle and runs straight forward another 21.0 meters in 5.20 seconds. Calculate his average velocity for each section of his hit and overall. What is his average velocity? All right, so this again is a problem of kinematics. We're interested in the motion of the football player as he travels along the field. So one dimension kinematics. So what is our object of interest? Well, we're interested in that football player. So that, well, spell right, B is our object of interest. Now for the first part of the question, we're interested in what is the average velocity during each section. And our second part of the question asks about the overall. Well, initially we're interested in at the start of the field. So when he gets that ball. So the start of the motion, gets the ball, starts running. And we're interested in what happens when he finishes running. It doesn't tell us exactly where he ends up, but at the end of the finish, and hopefully to a touchdown. Now we want to ask ourselves, especially for part A, what is this motion? Is it constant acceleration? Is he changing his motion during these intervals? What is the situation for his motion? And he is changing the motion. So we actually want to approach it, for part A, we want to approach this as three-phase problem. So it's a multi-phase, one-dimensional motion problem. So we need to define those three phases. So for phase 1, our initial and our final. For phase 2, we need to understand the initial and the final. And for phase 3, we need to understand the initial and the final. So for phase 1, well, it starts at the motion. He gets the ball. And it tells us that he runs for 15 meters. So we end at the 15-meter mark. That's phase 1. Phase 2, well, that's the end of phase 1, so that starts at the 15-meter mark. And it says he's pushed backwards 3 meters in that 1.75 seconds. So his final is at the end of being pushed back. Now our initial for phase 3 then starts at the end of pushed back, and it goes until the finish. So those are our 3 phases for part 1. Okay, so let's draw a picture. Here's our quarterback, and we'll call the beginning where he starts with that ball as x equal to 0. So I'm going to do the phases in 3 different colors. I'll start with the blue. So phase 1, initial position, final position, initial velocity of 1, final velocity of 1, acceleration of 1, and time of 1. My initial position for phase 1, well, that's at the start, at 0 meters. My final position, it says he runs 15 meters straight down the field. So that's our positive direction. So we ends at 15.0 meters. It then says straight down for 2.5 seconds. So I don't know the velocity initial. I don't know the velocity final, but since I'm interested in the average velocity across this motion, we can only worry about the average instead of having an acceleration in this example. And we said that he goes for 2.5 seconds. All right. What about phase 2? Well, my initial position for phase 2, final position for phase 2, initial velocity for phase 2, final velocity for phase 2, acceleration, and time, all for phase 2. So I'm using that 2 subscript. My initial position for phase 2, well, that's my final position from phase 1. So he starts at 15.0 meters. My final position for phase 2, it says that he then is hit and pushed 3 meters straight backwards. So he's pushed 3 meters in the opposite direction, 15 from those 3 meters, he ends up at 12 meters. Okay, so he's backwards 3 meters. We don't know the initial or final velocity in phase 2, but again, this problem is asking for that average, so we can look at that instead of considering the acceleration during that phase. And it says that this happens in 1.75 seconds. All right, well, what about phase 3? Well, similarly, we have an initial position for 3, final position for 3, initial velocity for 3, final velocity for 3, acceleration for 3, and time. So my initial position for 3, well, that's the final position on phase 2. So that's going to be 12 meters. It tells me that I run straight forward another 21 meters. So I go 21 meters beyond this 12. 21 plus this 12 is going to give me 33 meters. I don't know my initial velocity or final velocity, but again, I am interested in that average velocity as if there's no acceleration, and we do this for 5.20 seconds. All right, so these are my 3 phases. Now, what am I interested in? I'm interested in the average velocity for each one of these phases. So for phase 1, phase 2, and phase 3. Okay, well, we know that our final position is equal to our initial position plus v initial t plus 1/2 at squared. And when that's 0, this transforms into our final position is equal to our initial position plus our average velocity times time. So that's our definition of velocity. So this is what I'm interested in for each one of these phases. So for phase 1, my final position is 15 is equal to 0 plus v average times my time of 2.50 seconds. So 15 divided by 2.5, that gives me an average velocity of 6 meters per second. All right, for phase number 2, I'm going to use the same relationship as above. My initial or final position is 12.0. My initial is 15.0 plus v average times 1.75 is the time. And we get 12 minus 15 divided by 1.75. Our average velocity is equal to negative 1.71 meters per second. All right, remember I went back 3 meters, so our displacement was a minus 3. So that's where we got our final position of 12. And in phase 3, we have our final position of 33.0 is equal to our initial position of 12.0. That's that displacement. Our delta x, remember, was 21 meters, positive 21 meters, plus my average velocity times 5.20 seconds. And for phase 3, I get an average velocity of 33 minus 12 divided by 5.2, 4.04 meters per second. So my 3 average velocities for those 3 phases. Now part B of the problem asks, well, what is the average velocity across the entire motion? Well, that's not looking at these individual phases, but doing a problem that looks from the initial to the final. So let's do that. Let's look at a problem that looks directly from the initial to the final. And we can use some of the information we've gathered from our initial situation. I just want to have enough room. Erase this. All right, so we're going to kind of look at a pattern, or a problem that's not phases, but simply is where do we start? Where do we end? And therefore, what's the average velocity through that motion? Okay. So, that's lovely. All right. So, we are going to do this was part A. We're going to do part B. Because here's the same motion, and so our list for part B, we have initial, final position, V initial, V final, acceleration, and time. Now our initial position is at the beginning, so it's back at that 0. Our final position is the final location of phase 3, and we deduced that that was at 33.0 meters. Now, we don't know our initial or final velocity, but we're interested in the average velocity over that entire amount of time. Therefore, we're going to look at the average velocity without any acceleration periods. And what is our time? Well, our time is the total time it took to go through phase 1, phase 2, and phase 3. So we have 2.5 plus 1.75 plus 5.2, and we end up with a total time of 9.45 seconds. Now, like in the previous problem, we are interested in our average velocity. So x final is equal to x initial plus v initial t plus 1/2 at squared. But in the absence of an acceleration, this transforms into an equation that's going to be useful for our problem. So x final is 33.0, x initial is 0, v average is what I'm interested in, and our time is 9.45. So 33 divided by 9.45, we get an average velocity of 3.49 meters per second. All right, so a 3-phase problem and a single-phase problem in the same activity. Identifying your object, identifying that you have 3 phases that you're looking at, doing the list for each individual, recognizing the connection between the two, and solving for what we're interested in. Good job.